In this course, we'll look at what neural networks and deep learning are and how we can use them to gain valuable info from ambient assisted living datasets. So in the first few videos, we will have a short introduction to what neural networks are, how they work, and why they're useful. And then we'll see some examples of how we can use machine learning libraries such as scikit-learn and keras to apply these to various datasets. In other courses we've been introduced to different types of classification algorithms, which can separate data into classes based on different factors. Some of them are linear, so they use linear decision rules to decide which class a certain sample belongs to, while others aren't. The problem with using linear decision rules is that while they can be useful when the data is linearly separable, they can't do the same if the data isn't linearly separable in the space in which it exists. The first picture here shows us a linearly separable data. So, for example, we can say we have all of the red dots on this side, all of the blue dots are on this side. So maybe we can decide that this here is the separation boundary, which tells us, okay, everything right of this is blue, everything left of this is red. However, this won't work in the second picture, in which we have we have some red dots here, then some blue dots here, and then some red dots again. So we can just decide everything after this after some line is blue and everything before it is red, or the other way around. One way in which this can be solved is to map the data to some higher dimensional feature space in which the data is linearly separable. So what this means is that, for example, in the example that we had previously, we had a one-dimensional space, so we only had this x-axis, and we had to decide which x value tells us that the data that's greater than that x value belongs to one class, and the data that's less than that x value belongs to another class. For example, here we have a coordinate system, so a two-dimensional space in which we want to decide which dots are red and which ones are blue. If we can't separate the data linearly in this space, we could map this to some higher dimensional space, so we can add additional features which will make the data linearly separable. For example, here in the picture on the right, we have this plane. So we have this plane here on which we can which separates the red dots from the blue dots, or one class from the other. However, when we do this, so this type of mapping to a higher dimensional feature space isn't always the best solution. This is because in order to do this, we need to manually design these features that will make the data linearly separable. In order to do this, we need to have domain-specific expertise, and we need to put in more manual effort. So we would need experts from the field in which we're working, and it generally requires more work from us and from those experts than other types of classifiers. However, some of these classifiers work well or better than some other approaches. For example, using a linear perceptron, which we will get introduced to in one of these next introductory videos, often works better than the naive Bayes approach. However, this is only true for linearly separable data. So we want to find a way to make these some of these classifiers or these linear decision rules into something that can separate nonlinear data. So deep learning can help us learn features automatically, or it will help us do this by using nonlinear decision rules, which will be able to classify data that is not linearly separable, even though, which will help us perform classification with high accuracy for data that is not linearly separable. Deep learning is an approach used for neural networks. Neural networks are loosely inspired by the human brain. They are models which contain many connected units or nodes, which we call neurons. These neurons are connected, and so they're connected to other neurons, and they send signals to each other. So each neuron can send some signal, which is a real number, to another neuron, and then this neuron transforms the signal that it receives and then sends it out to the next neurons. One part of this transformation of the transmitted signal, or the real number, also includes the weight of the connection between the nodes. This weight adjusts during training, and this is actually so these weights are actually the parameters that we need to learn when we're training the neural network. That means that these weights actually change in order to achieve a higher accuracy for the samples that we use for training. Each sample is sent through the network, and then the output with the current weight is computed. And then if that output is wrong, then the weights are adjusted to bring the output closer to the correct result. The neurons that we use in the neural networks are aggregated in layers. That means that we have neurons which are so neurons from one layer are connected to neurons from different layers generally, and the signal moves from the input layer, in which we have the input data, to the next and then the next layer, until we get to the output layer, in which we get the result that we hopefully want.